Today we're going to learn about nonlinear functions and their graphs. So we call these nonlinear functions polynomial functions. And the thing you're going to want to know about a polynomial function is that it is the sum of terms where it's a constant times the whole number power of x. So you're going to want to spend time looking at the power on x, not the coefficients in front of it. So as long as we have a whole number power of x, which means you cannot have any fractions, you cannot have any decimals, you cannot have any negative numbers. They must be the whole numbers 0, 1, 2, 3, 4, etc. And they show you an example that 7 is a polynomial because it is the same as 7 to the x, 7 times x to the 0 power. So here are some polynomial functions. Notice the power on x is 1. The power on x is 5, 3, 1. So that's a polynomial function. Every term has a power of x. 2, 1, 0. 16. 4, 2. 3, 2, 1. Then these are not polynomial functions. Notice we have a square root on this one. Notice the power is a -3, a -4, and a -5. Notice these both have powers of 1, but they're not just a single term. They are two different terms. Here, notice that it is a 2, 1, 0, but it's in the denominator. So that's what makes it not a polynomial function. So let's see if you can decide from this list which ones are. Number 1 would be no. Why? Square root on the variable. Number 2, yes, because 4 and 2 are positive numbers. Number 3, no. Again, the square root. Number 4, no, because the power here is x, and x I can pick to be any number. Number 5, no, because I have powers in the numerator and denominator. Number 6, yes, the powers are only in the denominator, and they are 3, 2, 1, and 0. Number 7, yes, the powers are 5, 4, 3, 2, 1, 0. Eight, yes. Powers are 5, 4, 3, 2, 1, 0. 9, no. Again, a square root on the variable. So I'd like you to help define a polynomial function in your own words. The variable power must be a whole number. No square roots on the variables. No variables in the denominator. no negative variables, which does mean they wouldn't be whole numbers, and no variables as exponents. So you're just going to look at the variables and the powers on those to see if you have a polynomial function. So the degree would be considered the highest power used. So if the degree is 0, it's just a constant function. It reads y equals a number, so like y equals 2. Notice the power would be 0. A polynomial with degree 1 we call linear, and it would look like y equals 2x plus 3. A degree of 2 we call quadratic, and it would look like y equals negative 3x squared minus 4x plus 2. A degree of 3 we call cubic, and they would look like y equals 3x cubed plus 4x squared minus 2x plus 1. Also realize you don't need every single term in there. If I just had y equals x cubed, I have a cubic function. And 4 would be quartic, which would be y equals x to the 4th plus 2x cubed plus x squared plus x plus 1. And they don't have a 5th power, but 5th would be called quintic. Y equals x to the 5th. So the power has to have a 5. I could go plus 3x minus 2. As long as the highest power is 5, it's quintic. Okay? When we see a function graphed, we would call this an increasing function, because from left to right, as my x's increase, so do my y's. So if I pick these two particular points to look at, my x was 1, my x was 2. My x's increased, my y was 2, my y was 4, as my y's increased. Versus a decreasing function, which falls, and if I look at these pieces, as my x's increase from a negative 2 to a 1, my y's decrease. So it's a falling function. And a function can have parts that are increasing and parts that are decreasing. Where it rises is an increase, where it falls is a decrease. So let's take a look at some of those. Couple more terms. First of all, a polynomial function can have intervals that increase and decrease, which I just said. Each of these points of increase or points of decrease are called turning points. And we list the y values of the turning points as extrema. So we have an absolute maximum, which is an extrema, which is the highest point's y value. Opposite that would be an absolute minimum, which is the absolute lowest point's y value. Those are considered global extrema. Then we can have local maximum, which are all the y values of all the high points. And opposite that would be local minimums, which are the y values of all the low points. Okay, we're going to look at a graph, and we're going to find these different extrema on it. Okay. Notice, I don't know if you can tell, but this is a point, and this is a end point. So we're looking at this type of graph. To find a local maximum, I want to find the highest turning point. So do you see right here is the highest turning point? And the y value is 1, 2, 3, 4, 5. So y is 5. Then here we have another turning point at 4. And here we have a final end point of 8. Notice that endpoint is an absolute maximum, but not a local. Endpoints can never be local. They can only be absolute. Then I have 3 minimums. I have 2 local minimums at y value of 2 and at y value of 0.2. I have an absolute and a local minimum at -5 because it reaches the absolute lowest point on the graph and it is one of the low points. Only endpoints can never be local. A little bit more information. The degree of the polynomial will always be greater than the number of turning points. So if I'm looking at just this graph, I have 1, 2, 3, 4, 5 turning points. So the degree should be 1 more, would be a 6th power polynomial. So I just made a chart from before, so you can just use the one before and add to it. If the degree is 2, it meant we had 1 turning point. If I have a 3rd degree, 2 turning points. Now let me just show you a graph. A degree of 2 was a graph like this. So here would have been 1 turning point. A degree of 3, exaggerated, would be like this. So it has 2 turning points, 1 here and 1 here. A degree of 4 should have 3. So it could be like this. 1, 2, 3. A degree of 5 would have 4. So 1, 2, 3, 4. See, did I get them all? 1, 2, 3, 4. Need one more. 5. And etc., etc. All right. An even function is symmetric to the y-axis such that f of a negative x is the same as f of x. So here's an example of even. Notice here is my y-axis, which is a little difficult to see. But if I folded this on that axis, this would be symmetrical. So that means it's an even function. If I look at the table, f of 8 is -12. Or excuse me, f of -12 is 8. F of -8 is 10. F of 0 is 0. F of 8 is -10. F of 12 is 8. What this says is that f of x is the same as f of -x. So here is -x, here is positive x. Did we get the same y values? Again, here is -x, here is positive x. Did you get the same y values? So it is an even function. An odd function is symmetric to the origin, where f of negative x is the same as the opposite of f of x. Let me build a looking. All right. So if I look at this origin right here, this function, if I fold there, this function is symmetric around the origin. In other words, I could rotate it so it is identical on either side of the origin. So if I take this and fold it in there, this piece would fold into here. Algebraically, f of x equals, here's my function, x cubed minus 3x, if I'm looking at the function. So I want to test f of negative x. So if I put a negative in there, that's a negative x cubed minus 3 times a negative x. Negative x cubed is negative x cubed. And negative 3 times negative x is positive 3x. Now, if I take the opposite of this original function, it would be the opposite of an x cubed is a negative x cubed. And the opposite of 3 is a positive 3x. Is that the exact same function I got by sticking in a negative x? If the answer is yes, then it is an odd function. These two match identically. Okay? So determine where the intervals of the function are increasing and decreasing. State whether it is even, odd, or neither. So first of all, it is decreasing from here. Notice how this is going off the graph, so I'm not going to put arrows on anymore. You have to understand when it's going off the graph. If it's an endpoint, it should be stressed as an endpoint. If you question, it's all right to ask, is this an endpoint or an arrow? So my function is decreasing all the way to this point. So it is decreasing from negative infinity to 3. And when we list where they're decreasing, we use the x values, the domain of decrease, different than the extremas. The function is then increasing from 3 to 8. Oh, and this should be inclusive because it is equal at that point. So from 3 on to infinity. To be even, it must be reflexive across the y-axis. Is this function reflexive across that? Nope. To be odd, it must be symmetric around this point. Is that function even symmetric around that point? Nope. So this would be neither even or nor odd. Okay, let's try this one. Function in decreasing, again going off the graph all the way to this point. So decreasing from negative infinity to 0, inclusive. Then it increases on the other side. So increasing from 0 to infinity. To be even, reflexive across the y-axis. Can I fold there and get the same function? Yes, so it is even. This one? Decreasing here again off the graph to this point, which looks like negative 1, negative 2.5 about. We're estimating here. So from negative infinity to negative 2.5. Then we're increasing here. And that looks like about 0.2. So we're increasing from negative 2.5 to negative 0.2. Then we decrease again. And we're not quite at 1, let's say about 1.8. So from negative 0.2 to 1.8. And then we're on an increase again from 1.8 to infinity. And that takes care of my entire function. Then, if it's even, it's reflexive over this axis. Is that reflexive? No. I meant symmetric, sorry. Is it symmetric over that axis? No. If it's odd, it is symmetric around this point. Is it symmetric around that point? No, it doesn't even go through that point. So again, this is a neither even nor odd function. But if they're given to you algebraically, to see where they decrease and increase, you're going to have to put it on your graph. And I know that the graph of a cube root should look like this. Okay? So it's increasing to 0, but it doesn't actually turn, it just keeps increasing. So it isn't only increasing from negative infinity to infinity. No matter what, the function is always on an increase. It never falls from left to right. So if it's an even function, if I put in a negative x, I should get the same function back. So let's put in a negative x. So I have the cube root of a negative x, which is that same thing, the cube root of a negative x. Is this function, let me change colors, the same as my initial function? No. If it's odd, let's see if it's the opposite. So if I take the opposite of the function, it would be negative of the cube root of x. 3 negatives, does that make 1 come out? That would be yes. So are these two functions, identical? Yes, they are. So this is an odd, oh my gosh, function. Okay, let's state the local and absolute extrema. So let's first find them. Turning point, turning point, turning point. Off the graph so they don't reach absolute height with that part. So in this case, the absolute max, it never reaches an absolute highest. So there is none. An absolute min, where does it reach the absolute lowest point? And that would be what y value, and it looks like there. So let's say it's about 1.8. A local min, or excuse me, max, let's do the max first. Okay, it reaches the highest point right here at 5. A local min are all low points. So we had one at 1.8, and we have another low at about 4.8. And you can put about on those since we're estimating. Does that make sense? Okay. That looks like it. You can try your homework and see how it goes for you.